Okay, now let's see Fourier transform as an application that can be used in diffraction experience. Here we go back to Fraunhofer diffraction situation where we have diffraction aperture plane. Okay, and here it is the points on this plane is represented by small xy, and you have a point Q on the plane. The vector from the origin to that point is r. Now we have a focusing lens, and on the focal plane of the lens we have the Fourier plane, and we want to see the distribution, intensity distribution on the screen in general, and maybe at the point P. Here the points are capital X and capital Y. Capital Y. Okay. What is the purpose? Because when we were dealing with Fraunhofer diffraction, we have used we have found using Kronecker formula. We have seen the Fraunhofer diffraction from an aperture. Then we used it from a slit. Then we have used it from a straight edge, and so on. Okay, it had different definite shapes. Now, in this case, we don't have. We are trying to look at um, an aperture of arbitrary shape. It can have varying phase across it, because suppose you have your uh, aperture is masked by a piece of glass which varies in thickness across all this, and in that case you will have different phase values as the beam comes out, and also any arbitrary shape in phase amplitude it can vary, or it is probably some coatings over the aperture so that there is a gradient in one direction of intensity, gradient of intensity coming out in one direction, and so on. Whatever be the case, you can incorporate that into what we call the aperture function. And you have seen that Fourier transform of the aperture function will give you the diffraction pattern at the Fourier plane. And therefore, here we are going to consider a Fraunhofer diffraction. The aperture with arbitrary shape, that is what I said just now. The aperture with arbitrary transmission, including phase retardation, which may vary across the aperture. Whatever be the case, our aim should be to find or to define an aperture function. Just take the Fourier transform. As I said, we to small xy in the aperture plane and large xy, capital Xy in the focal plane. Then rays leaving the diffracting aperture is specified by the direction cosines alpha, beta, gamma. All these rays are brought to a common focus. As I said, the parallel rays will be brought to a common focus. P. Okay, you have rays leaving from Q, and it is reaching the point, and X is L tan alpha or L alpha. Here L is the focal length of the lens. Then Y is L tan beta. Or alpha, beta, gamma, the direction cosines. Now, the path difference between a point Q or a rays coming from the point Q and O is given by R dot N, where N is the unit vector perpendicular to the aperture. Here R is what? R is this one. This vector here, which is okay, you have X component, Y component along here, and therefore R is X plus IY or Xi plus Yj. Then N in terms of the direction cosines, alpha I beta j plus gamma k. Therefore R dot N is this one. What is that R dot N? Path difference. Now if you use the approximated Fresnel-Kirchhoff integral or Fresnel-Kirchhoff formula for the case of Fraunhofer diffraction, which we have used in the past, and simply substitute for delta R, but delta R is R dot N, and therefore it is this quantity here. And if you do that, you will get integral I k x xl y y, and we can further simplify it as we did in the past, but still it is, for now, let's say it is good enough. It is coming to a form very similar to a two-dimensional Fourier transform. That's why here we can we haven't given the limits of integration, but with appropriate aperture functions we can add the limits. Okay. And this formula by itself is the case of uniform aperture, or in other words, there is no variation across the aperture. For non-uniform aperture, we introduced something called gxy. It's called the aperture function. This aperture function is introduced like this: uxy gxy to the power x. And there I can also introduce dimensionless variables like this, what we have done in the past. And here, what is that? That is mu x k mu y, mu x plus. And if you consider these are spatial frequencies, then the whole expression here is the Fourier transform, 2D Fourier transform of what? Of the aperture function, of this function here. And therefore, what is this one? This is the field distribution on a screen, and at a distance x, at a distance equal to the focal plane, and that is the Fourier plane. Okay. Here this distance is the focal length of the lens. Okay, that's what we say here, focal plane of the lens. At that plane, the intensity distribution will be like this one, or sorry, not the intensity distribution, field distribution will be according to this equation, or that is a Fourier transform of sorry, we are further down. It is this one, and that is the Fourier transform of the aperture form of gxy depends on what type of aperture we have. Or in other words, u, mu nu and gxy are called the Fourier transform pairs. This is, as I said, the diffraction, therefore, is a Fourier transform of the aperture function. Here, we have a key point here, which is the field distribution in the Fraunhofer diffraction pattern is the Fourier transform of the distribution across the aperture, called the aperture function. That is your result. And therefore, once you know the aperture, once you know the shape or the phase or the optical densities of the apertures, we can simply get the pattern on the Fourier plane as by taking the Fourier transform of the aperture function, which is normally a two-dimensional function, and therefore u, mu nu and gxy are Fourier transform pairs. Yesterday, I have watched a movie on YouTube, which is which gives an alternative approach to prove the above. If you just search Introduction to Fourier Optics or follow the link, you could get get to the video. Here it is. I thought it was quite nice. Here, what he has done is consider a plane where you have apertures. In this case, he has two apertures, aperture 1, aperture 2. You could have as many apertures as you like. To start with, we don't make any restrictions on how many apertures that you have. And this apertures, okay, this is your x direction and this is your y direction, and therefore let's say these are slits in the YZ plane. Okay, these apertures are slits in the YZ plane, small y, small z. Here on this screen or on this aperture plane, you denote the points by small x, small y, and therefore here is your origin, that is 0, 0. Here you consider a small element dy, which is at a distance y from the origin, again in the same plane of and therefore x remains 0. What we are trying to see is to calculate the field distribution at a point P on a screen, which is denoted by capital X and capital Y, due to this tiny element dy on the aperture plane. Okay. That is, and then once you have that, you can integrate it to get the intensity distribution due to this whole aperture or any number of apertures. Okay. Now for that, we consider this is your common origin, and let's say the distance from here, from this origin to the point P is denoted by the vector capital R, and from the center of this tiny element, length element, to this point is small r, vector small r, and this angle here denoted by theta. I think now I have described the experiment or the situation. Now, one of the things that we take for granted, at least at this point, is that radiation from a dipole. If you had a radiation from a dipole, the electric field at a distance r would have been proportional to 1 by r. That is due to its spherical symmetry, because and also the conservation of energy. And if you integrate it over 4 pi r, it will be 1 by r times 4 pi r, that is constant always. In a similar way, for a cylindrical symmetry, like if you had a very large cylindrical source that emits radiation, then the electric field at distance r is proportional to r to the power half. And therefore the intensity, okay, what will be the area? Area is something 2 pi r times the length of the cylinder, and when you if you consider the intensity, then that intensity, the conservation of energy will require that this r and this r half square and the denominator will cancel out, and you will get the conservation of energy. Okay, the idea here is we consider the slit as a very long or an infinite cylindrical source in the YZ plane. Okay, in the YZ plane, and therefore EP is r to the power half, or at the point P, the electric field. Okay, we used to use U. Just take it. Okay, I should have used UP to be consistent, but let's say this is the same as UP in vectorial form, and this is the person has used EP. That's why I didn't think twice. Okay, now C is a constant, and keep it. We'll use it later. In the figure, okay, there are two aperture sources shown, but you could use any number of sources. Now consider a small element. Okay, I have explained all this. Now let's see what will be the field at P due to the source of length dy. Let's denote it by the field, a small field dEP. As we said, it is C over r to the power half times, since it is a traveling wave, e to the power ik dot r minus omega t. So k is the wave vector and omega is the frequency of that light. Okay, nothing special about it. This is if you remember your electrodynamics courses, you may have done the dipole radiation and you may get similar results there with this replaced by 1 over r, I think. Okay. Now we try to make some simplifications. What is r? R is the magnitude of the vector r, and if you consider this triangle here with this thing, you have theta, and what is this? This is distance small y, and this is distance capital Y, and therefore this part here is y minus y, and therefore r square is this is x square plus y minus y all square, and that is okay. That's what I have written here, x square root of x square. Now you just expand it, take r out of the thing being a large quantity. Now, okay, this is because x square plus y square is r square. You can see from the figure. Now, since r is going to be very large compared to y, we can straight away neglect this term, and therefore what you will get is r times square root of 1 minus 2 y over r square, and using this expression here when epsilon is much less than 1, you can cancel out 2 with the denominator at the denominator 2 there, and that is it, 1 minus 2a. Substitute it for r. Okay, now there is a thing. In principle, because compared to y and y, r is going to be much larger, and you can, certain cases you can approximate it by r again, because it's not going to be very different from what it is, because y is going to be small, y is going, small y is going to be small, because we are taking the refractive in the diffraction, and the screen is in the far field. Okay. That is what I have done here. But here I have used the whole thing. I'll explain to you why. Because okay, and here we have taken ikr out and omega t, combine them, kr minus omega t. Then we have this function, this value. Here we wanted to keep this product y because of this k is not standing by its own compared to r. It is multiplied by k y over r. This is what this term is, and k is normally a very large number, because that is k is 2 pi over lambda, and that is lambda is of the order of 500, visible case 500 times 10 to the minus 9 meters, or that is, what is it, 15.2 times 10 raised to 7, and therefore a very large quantity multiplied by a small quantity, and therefore as a whole this term could be significant. That's why we keep that term. Okay, now you have an expression for DEP. What is DEP? It is the field distribution at the point P on the screen due to a small element dy on the aperture, and the total field can be at point P can be obtained by integrating over all the apertures, because apertures are the places where it is open for light, and only those apertures will contribute to uh, uh, to the intensity pattern on the screen. That is logical, and also we have proved it in the past. It's only the apertures during the initial stages of starting the derivation on diffraction. Now I'm going to make a small substitution here, because here we have y over r, and that is sine theta. Okay, you remember what theta is. Then ky sin theta is k sin theta, or that is k sin theta is the component of k in the y direction. Okay, k cos theta being the component in the x direction. And therefore we can write it like this. The field, total field at the point P is, okay, remember this is your UP, scalar P that we have been using all the time. Only for this particular top section I have used EP, but you shouldn't confuse it with UP. And this is C over R to the power half, and a term here plus times integrated over all the apertures e to the power I k y d. Now this is something that is of that doesn't have much interest to us, because it says time. It tells you the time oscillations of of UP, EP, and so on. But this term here will give you the spatial distribution in the direction of y, and therefore what we'll see is we will concentrate on this is actually the intensity distribution. EP is actually a function of y and t. It gives you the y and t, and this y comes through this ky. What was ky? That was ky was k capital Y over r, and that will give you, it's as a function of capital Y and t. Now we are going to eliminate t, and therefore only interested in the spatial distribution of intensity, at least at this point, and therefore that will be C over R to the power half. You want to keep that because it will give you the R dependence, and also this this function here is varying between plus or minus 1, and that will act like a modulation of to this function, and that's why we are interested only in the intensity distribution. Therefore this is what you will get for the spatial distribution of intensities. We could now define an aperture function. Okay, define an aperture function where it is C over R to the power half times some f. What is f? Okay, if it is rectangular aperture or whatever be the aperture, f equal to 1 for those regions whichever is open, and f equal to 0 for those regions that are not open. Or f equal to 1, we will put f equal to 1 for those regions where you have light coming through, and f equal to 0 if there are no lights. Okay. What is okay, on a big screen you have certain holes, and those holes will be represented by 1 and the blocked regions are represented by 0. And therefore, we can write this spatial distribution E0 as integral or apertures ay times e to the power I k y y dy. Okay. Now, it's again integration over all apertures. But since we have defined something like an aperture function like this one, doesn't really matter whether we integrate over the apertures or over the whole space, the whole screen. Okay, only those regions that are open will contribute to this integral. Even if we integrate from x from minus infinity to infinity, y from minus infinity to infinity, then only those regions, these regions will contribute. All the rest of the regions will not contribute. The rest of the regions will not contribute anything to the, and therefore, instead of having the integration over the apertures, I'm going to integrate over minus infinity to infinity. Therefore, the field distribution on the screen is integral minus infinity to infinity, the aperture function times e to the power I k y. And this is nothing but the Fourier transform of the aperture function. And that proves that the 1D electric field distribution on a distant screen is the one-dimensional Fourier transform of the aperture function. And this can be generalized to 2 dimensions. And you can do this as an assignment, like diffraction from a single slit and rectangular aperture. Find the diffraction pattern using Fourier method. So we have done that, a single slit. Maybe you can do for rectangular aperture, which is a 2-dimensional Fourier transform. It is reasonably straightforward to do that. Okay. Thank you.